This robot could not trust its own position. The tires slip. There were no wheel encoders, so this robot had no choice but to look at the world. 4 motors salvaged from a used hoverboard, a 40-kilogram autonomous mobile robot powered by ROS 2 and 3D LiDAR. The standard configurations for autonomous mobile robots. I tried them, found their limits, and discarded them, built only with what survived that process. In this video, I'll take you through the details of this project, breaking it down into hardware and software. Step by step. I've included the GitHub links for the code and 3D models in the description below. So please check them out if you're interested. On this channel, I've mostly shared music-related projects using stepper motors and solenoid valves. So seeing a robot all of a sudden might come as a surprise. But to me, it doesn't feel like a completely different path. Ever since I was creating sound with stepper motors, I've always been thinking about how to control a motor, how to synchronize them, and how to observe their states. This time, the subject just changed from sound to a 40-kilogram mobile machine. And this machine, carrying 4 brushless motors, will also have its day to make sound. We'll get to that in a later chapter.
Destination reached.
Let's quickly go over the main configuration of this robot, which I call SSR, Skid Steer Robot. The drive system splits 4 hub motors between 2 FSESCs. The front and rear power supplies are completely independent. The PC is a Geekom GT1 Mega, running Ubuntu 22.04 and ROS 2 Humble. For sensors, it carries a Livox Mid 360 and an Oak DS2. The motor side uses 2 separate systems of hoverboard batteries. Power for the PC and peripherals is consolidated into an EcoFlow Trail 300 DC. I've also inserted an EDLC into the PC line for power stabilization, LED strips, a USB speaker, and a DualSense controller. These systems do not run under a single unified program. They operate independently, so even if one part crashes, the others keep running. Why this architecture exists will all connect in a later chapter. Now, let's see how these components interact. Step by step. When designing an autonomous mobile robot, the safest choice is to use geared servo wheels with high-precision encoders. But I didn't choose that pre-packaged route. Instead of assembling a standard kit, I wanted to build the drivetrain, the very foundation that defines the robot's performance, with my own hands. For the drive source, I chose hub motors from used hoverboards found on the secondhand market. Originally designed to support and carry a human in the 100-kilogram class, these motors, when distributed across 4 wheels, have a margin that can withstand a load of over 50 kilograms per wheel. The 8.5-inch off-road tires, with their deep tread and wide contact patch, met the specifications needed to handle obstacles. Plus, having 4 of these 8.5-inch tires lined up just looked flat out good. For a robot, I believe appearance is part of performance. However, this choice came with a clear penalty. These hub motors have no encoders to track rotation. Inside, there is only a simple Hall sensor to measure magnetic pole position. In other words, the moment I chose this structure, reliable wheel odometry was off the table. How to overcome this missing positional information became the ultimate theme for the software architecture. To control these mystery motors, I turned to FSESC. With nothing but a fragmentary 300 watts written in the hoverboard user manual, you can't even get the motors to spin. Winding resistance, inductance, and the torque constant. The ability to auto-tune these parameters right on the driver's side was absolutely essential. On top of that, its open-source firmware could drive these motors on their Hall sensors alone, with no external encoder. That openness was exactly what my encoderless setup needed. The chassis layout is a four-wheel skid steer, rather than a common differential two-wheel drive. In this system, which lacks a steering mechanism, keeping all four wheels firmly on the ground is a lifeline. When turning solely by the difference in left and right rotation, if even a single wheel lifts, the balance of driving force collapses. The front features a double wishbone, independent suspension, while the rear uses a rigid axle. A suspension system repurposed from electric skateboard parts absorbs road imperfections, constantly pressing all four tires onto the ground. The red coil springs are not just functional, they also serve as a visual accent. The frame was built using 25mm square aluminum profiles. I designed it in SolidWorks, optimizing the suspension mount positions and weight distribution on the 3D model. After assembly, the readings from scales placed under each of the four wheels were exactly 10 kilograms. It achieved a perfectly even balance, front to back, left to right. Integration of the drivetrain system is done via CAN bus, 2 FSESC 4.20 duals. 4 motor drivers, each assigned a CAN ID, connect to the PC through an SHC 30G USB to CAN bus adapter. The physical chassis was now complete, but without manufacturer data sheets or encoders. How do you control these 4 hub motors smoothly and accurately from ROS2? Next, we'll look at how I drive these motors and how I observe them. Spinning the motors itself isn't that difficult. The real challenge was observing exactly what was happening inside while all 4 motors were running simultaneously. Drive while observing, observe while tuning, building those tools right into the robot. I made up my mind during this phase that this was the core of the development. Hoverboard motors are brushless, DC motors, and to run them smoothly, you need vector control, FOC, field-oriented control. But to make FOC work, you must know detailed parameters like winding resistance, inductance, and flux, none of which are disclosed by the manufacturer. That's where I leveraged FSESC's auto detection feature. Using a software called FSESC Tool, I spun the motors on the spot to measure their characteristics, turning black box hardware into controllable numbers. One by one, the system connects 2 FSESC 4.20 duals via CAN bus. Commands from ROS2 reach the 4 wheels over CAN, while statuses like RPM, current, voltage, and duty cycle stream back in reverse in real time. To log this data as a CSV, I wrote a tool called canmonitor.py. I also created odomlogger.py to record the odometry from FastL-IO2. With these, I could precisely align the commands sent to the motors with how the robot actually moved on a timeline. When I lined up the data, I discovered something fascinating. The 4 motors salvaged from used hoverboards all had different characteristics. In particular, the front left motor had a lower flux linkage value, which represents magnetic flux strength compared to the others. As a result, even with the exact same command, the front wheel would start spinning faster during acceleration. It wasn't just a gut feeling like, the front feels a bit snappy. The data explained it with clear logic. Even when pushing into higher speed zones, data, not intuition, was the main character. When the top speed reached about 32 kilometers per hour, the log from canmonitor.py showed that the duty cycle was pegged at 95%, and the battery voltage had dropped by nearly 7 volts from its pre-run 39 volts. That wasn't a glimmer of hope saying, it'll go faster with a bit more tuning. It was the data declaring a hard physical limit. Entering a speed regime, a full order of magnitude higher than industrial AMRs. The chassis began to scream. During a high-speed test, an accident occurred where the front right motor burned out. No footage of that exact moment exists. But the drive data survived. Analyzing the log, I found that the front left motor failed to brake properly during deceleration. The individual variation from acceleration likely triggered a behavioral collapse under extreme conditions, leading to the crash. Without the data, I wouldn't have even known what happened. Grounded on this data, when rebuilding the machine, I reassigned parameters to the front left motor, so it would behave identically to the others. Once you observe it, you can tune it. The strategy set at the beginning of this chapter came full circle here. The mechanism to drive the motors, and the mechanism to observe them. With these two pillars in place, I could finally understand the vehicle's behavior logically. Yet, says no matter how much I decoded the drivetrain data, an unresolved problem remained. When the tires are slipping on the ground and tearing through physical limits, the wheelside data can no longer serve as proof of where the robot is. If you can't trust the wheels, you have to look directly at the outside world. Next, we'll move on to self-localization using LiDAR and an IMU. In Chapter 1, I mentioned that wheel odometry was impossible. In Chapter 2, I explained that the wheels couldn't tell us where the robot is. This chapter is about how I faced that reality and what I chose to trust as my sole anchor. A typical mobile robot relies on wheel encoders to calculate its position from tire rotations. However, a four-wheel skid steer structure naturally forces the tires to slip sideways during every turn. Even if you had encoders, the moment they slip, the values drift away from reality. By choosing this chassis, the information from the wheels was destined to be useless for positioning. What remained was LiDAR and an IMU. I began exploring ways to combine these two inputs to pin down an unshakable position. First, I tried SLAM Toolbox, which is widely used in ROS2 for mapping and real-time localization. I forced the 3D point cloud from the mid-360 into a 2D format, but the results were disappointing because the points seen by the mid-360 shift with every frame. Converting it to 2D severely cut down the data density, causing the matching to fail. I tried it and discarded it. Next, I tried AMCL, an algorithm that matches point clouds against a known map, but this too hit the wall of 2D conversion. And worse, it triggered a conflict over who gets to publish the TF, the coordinate transform tree. Multiple nodes inside the robot tried to overwrite the same coordinate system independently. The position on screen started jumping violently. I tried it and discarded it. I also tried another framework called SKRM, built for Chinese Sentry robot competitions. It integrated Fast Leo 2 and Nav2, a configuration remarkably close to what I wanted, thinking it would save time. I built it in a dedicated workspace and tested both its mapping and localization modes, but the assumptions were too different. SKRM assumes a 3D point cloud PCD map format, which completely clashed with the 2D occupancy grid PGM map I wanted to run. Positional correction only happened once at startup, rather than continuously during a runtime. The TF structure was also highly proprietary, making the cost of aligning it with skid steer and FSESC higher than building it myself. No matter how polished a framework is, if the core assumptions don't match, reuse fails. Through all this trial and error, I returned to a single conviction, and that was my absolute trust in the Livox Mid 360 sensor itself. With this sensor, before starting this project, I had been evaluating a system called Fast Levo 2, which integrates LiDAR, IMU, and a camera to generate colored point clouds. That's how I happened to have a mid 360 on hand. During that testing, what struck me was how stable the system was. The drift was incredibly small. If I could unlock the true potential of this sensor, it might open up new possibilities for AMRs. I had a strong hunch. So, I made a decision, moving away from the Levo 2 line that integrates vision to the Leo 2 line that strips it away. Instead of burning compute on visual processing, I would trust everything to the spatial geometry of the LiDAR and the inertial data of the IMU. I chose Fast Leo 2. No need for extra features like loop closure to clean up the map. I just focused on one thing: low drift observation that would almost never lose track of its position, even during high-speed runs exceeding 30 kilometers per hour. Strip away the noise and sharpen a single function. I restricted the TF publishing strictly to the Fast Leo 2 system and wrote a custom shim, a bridge code to clean up the data formats, just like the monitoring tools in Chapter 2. I baked in a mechanism here to automatically detect the exact moment a coordinate jumps for obstacle detection. I introduced STVL, Spatio-Temporal Voxel Layer, which handles 3D data natively. Without crushing it down to 2D, the system uses the world exactly as the mid 360 sees it, at full resolution for path planning. Stairs, desk legs, pedestrians. What is seen in 3D is processed in 3D. I began test runs with the completed system. Even after hours of driving, the coordinates never jumped again. The system to keep the robot from losing its way was finally working. However, knowing where you are and being able to follow a path to get somewhere are two different things. Next, we'll move on to path tracking, following that position. ROS 2 comes with a standard navigation stack called Nav2. You give it a goal on a map, and it plans a path and issues velocity commands to follow it. However, Nav2 is not designed out of the box for the specific behaviors of a four-wheel skid steer. Left stock, as the robot gets closer to its target, it gets confused and tries to make unnatural, jerky pivots on the spot. To bridge this gap between hardware and software, I decided to rethink the controller. The default DWB local planner just didn't cut it for this machine's speed and characteristics. After endless trial and error, the one that survived was Regulated Pure Pursuit, or RPP, which specializes in pure path tracking. Right around that time, I learned about an evolution of RPP called DWSP, Dynamic Window Pure Pursuit, which had just been published. Proposed by Dick West from KO University. This algorithm combines the tracking stability of pure pursuit with the dynamic velocity and turning constraints of the dynamic window approach. How to handle the aggressive, forced pivoting of a skid steer smoothly within its physical limits. I integrated the philosophy of DWPP as a custom patch and spent days adjusting the look-ahead parameters, fine-tuning exactly how far down the path the robot should peer, right on the real machine. On top of that, I layered a speed filter, allowing the robot to automatically throttle its maximum speed based on specific zones on the map. These are all critical layers of safety, designed to keep a 40-kilogram machine completely under control. The robot could now localize and track its path, but keeping it running reliably day after day is a whole different story. Next, we'll talk about system operations. A large system never fails in just one place. Tiny operational bugs pile up over time until one day they bring the whole thing to a halt. That's why system stability isn't about finding a single silver bullet. It's about stacking layers of defenses. A ROS 2 environment running nearly 20 nodes simultaneously, complex startup sequences, and unstable power supplies. I had to pin these down, one by one. First, environment management. Launching this many nodes individually is completely impractical. Using a terminal multiplexer called TMUX, I created a system to launch 12 windows of bundled nodes all at once via a single script. Each window acts as a portal to monitor the health of specific nodes. Never lose sight of what is happening inside. That was the discipline I forced upon myself. I also isolated the workspaces into 3 separate entities. One for the LiDAR, one for FastLeo2, and one for the SSR core. After a painful experience where mixed dependencies caused days of build errors, separating the environments was the only way to maintain system purity. Next, locking down communications and connections. The CAN adapter or the controller changing its device name every time it's plugged in, or the communication libraries hanging outdoors when there's no network connection. To eliminate these variables, I fixed the device names using UDEV rules and built a virtual network interface inside the PC. It's unglamorous groundwork, just to ensure it boots the same way every single day. And then the power supply. While powering the system from a portable battery via a PD trigger cable, I was hit by random, sudden PC shutdowns. No physical button was pressed. Yet, when I analyzed the OS logs, a power button reconnection was recorded right before every crash. A PD trigger pulls 20 volts from a USB-C port, but if that output fluctuates even a fraction, the PC misinterprets it as a power button press. In short, an electrical ripple was being translated as a physical button press. Once you see the cause, you can implement the cure. I placed an EDLC, a massive capacitor, into the PD line to physically absorb those microdrops and isolated the power feed for the LiDAR, pinpoint the cause with data, and fix it with hardware. The exact loop from Chapter 2 repeated itself here, this time at the very foundation of the system. Since then, it hasn't shut down a single time. The EDLC itself was something I salvaged from another project. At 34 volts and 54 farads, it was total overkill for this application, but it was the fastest path to stability. Environment, connection, power. Each is a separate thread, but if even one snaps, daily operation falls apart. It's not flashy tech, but the accumulation of this tedious groundwork is what forms the bedrock of keeping a massive system running. By this point, the system was running rock solid. However, some of these tools serve a double purpose. RVs, the dual sense, AVAs, and the LEDs. These are also the channels that take what's happening inside the robot and translate it back to us humans, using light and sound. Next, we'll talk about the interface where robot and human connect. A 40-kilogram rigid body, silently approaching at speeds over 30 kilometers per hour before even considering its performance as an autonomous robot. That is a potential physical weapon. That's why this robot needed a voice and light to signal its state to the surroundings. At the heart of this is AVAS, Acoustic Vehicle Alerting System. This robot features a built-in system that synthesizes audio in real time, synchronizing with the driving speed and motor RPM. Instead of a generic warning buzzer, I poured in trial and error to craft a sound signature similar to modern EVs. Back when I was making music with stepper motors and solenoids on this channel, my struggle was how to make the motor sing. That experimentation came all the way around to serve as a safety device for this robot. It's the ultimate convergence of what I teased in the channel intro. The day it makes sound. Though this time, I didn't hack the motor's own electrical whine, opting for an audio system routed through a USB speaker. The simulated acceleration sound is not just theater. How much torque is this 40-kilogram machine putting down? How fast is it trying to go? It's the sonification of telemetry data, letting humans understand the machine intuitively. For auxiliary vision, it also carries an OAK-D S2. However, on this robot, the camera is not used for self-localization. The anchor for positioning remains strictly the LiDAR and the IMU. What is left to the OAK-D is person detection.
Person detected. Person detected.
A neural network runs natively on the camera's dedicated Myriad X processor, detecting pedestrians ahead. The detection results stream into ROS2 and are overlaid directly onto RViz. In the future, this will interface with AVAs and the LED strips, allowing the robot to actively alert people of its presence. But right now, the detection trigger is way too sensitive, causing the siren to sound continuously. So for now, only the visual overlay is active. What to automate and what to leave to the human operator. Here too, the judgment of what to trust and what to discard continues. The lighting cues have also been organized. The LED strip on the underbody shifts, colors in sync with the vehicle state and AVA's audio. The front and rear LED strips flash to signal mode transitions, like stopping or warnings. These LEDs are managed by an Arduino, receiving serial commands sent from the PC. For manual intervention, I adopted a DualSense controller, even if autonomous operation is the main goal. Manual override is essential for maintenance or emergencies. This robot alternates between two modes: autonomous navigation via Nav2 and manual control via the DualSense. Pressing the options button drops it into DualSense mode, instantly overriding velocity commands from Nav2, bringing the robot to a dead stop on the spot. From there, the operator takes direct control. You can manually steer around obstacles or nudge its position. Pressing the Create button snaps it back to Navi 2 mode, allowing the robot to pick up the interrupted path right where it left off, resuming autonomous operation. It just starts running again, as if nothing happened. In commercial AMRs, these safety override functions are often hardwired into dedicated hardware or complex control loops. Here, a single controller handles it all. This behavior flowed naturally out of ROS2's control mode switching mechanism. It wasn't even a feature I explicitly designed from day one. Let's take a look at how the inputs are mapped in DualSense mode. The L2 trigger acts as a dead man's switch, meaning the robot only moves while it's held down. Let go, and it stops. This is the ultimate safety line for human intervention. On the other side, the R2 trigger is mapped to a boost, letting the robot brake past its normal speed limits. While pressed, the controller buzzes continuously with haptic feedback. You are stepping into the danger zone. That signal is fed directly back into your palms. Feeling the physical limits I used to read in the logs back in Chapter 2, now right in my hands. I shrink the distance between human and machine. Additionally, the D-pad and R1 or L1 buttons are assigned to specific audio triggers, like sirens or sound effects. If you need to alert a pedestrian, or just want to give the robot some character, the operator can actively trigger sounds. It's an intentional path of expression, separate from the automated AVA's audio. This DualSense plays yet another role. While driving manually, pressing the triangle button temporarily drops a waypoint at that exact spot. Then, circle confirms it, or X cancels it. This two-step safety window prevents stray points from polluting the path. By registering them sequentially, a clean navigation route is stitched together. Finally, pressing the square button exports the entire string of waypoints as a YAML file, passing that exported YAML to a playback script called WP Player. The robot begins retracing the exact route you taught it. Intervention, signaling, and route teaching. The exact same controller wears all these hats. Watching over all of this is a customized RViz to endure long hours of monitoring. The entire UI was tuned to an eye-strain, friendly dark theme. Meanwhile, to ensure cost maps are never missed, the viewport remains white, flanked by custom meters comparing command velocities against real-time speeds. This is designed for the human element, optimizing the layout not just for the robot, but for the person watching it. AVAs, the LED strips, the dual sense, RViz, and the OAK-D person detection. These are not a single, monolithic application. They run as independent processes. Instead of calling each other directly, they broadcast events across ROS topics. For example, when WP Player signals a waypoint arrival, AVAS fires an arrival chime, and the front and rear LED strips flash in unison at that exact millisecond. I built that synergy completely over topics, independent architectures, bundled into a single experience via topics. They point in different directions, but they all share the same goal: creating a data pipe between robot and human, carving a window of interaction into an otherwise soulless machine. Only when this contact layer came together did SSR cross the line from a simple moving machine to a truly trustworthy autonomous robot. Across all 6 chapters, we have looked at the building blocks that shape this robot: physical structure, motor control, self-localization, path tracking, system operations, and the interface with humans. These are all running realities, active inside this chassis right now.
Passing waypoint 1.
But this is just one approach, and the SSR project is still evolving, separate from the physical robot. A few parallel experiments are already underway. One rebuilds SSR inside NVIDIA Isaac Sim, keeping the same ROS2 control interface between simulation and the real machine. Another explores vision-only self-localization with a Z stereo camera. This time, I staked everything on LiDAR, but visual tracking remains a path worth investigating. Different bets, running quietly beside the main build. The software on this robot stands on the shoulders of countless open-source projects and the wisdom of those who came before. The FL_Navi2_helper by Atraklab and Rashid, which became the foundation for the Navi2 integration. DeQuest from Keio University, who provided the core philosophy for correcting four-wheel skid steer behavior. Benjamin Vetter, whose VESC project powers the entire motor control toolchain. And the Mars Lab at the University of Hong Kong for Fast Leo 2, which serves as this vehicle's eyes. If even one of these was missing, SSR would never have taken shape. As a small return to that community, I am publishing the entire development journey on GitHub. What I am open sourcing is not just code. It includes Navi2 configurations that couldn't fit into the video, 3D models, and the raw scars of development I've wrestled with, the patches, the logs, and the parameter matrices. If the trail of my trial and error can become a stepping stone for someone tackling a similar build, that's all I can ask. It's published under the MIT license. Like the development journey itself, this robot is still unfinished. There is still room to grow. In the opening, I described this as a process of deciding what to trust and what to discard. I discarded wheel encoders and trusted the LiDAR. I discarded default packages and trusted custom patches and my own tools. What to trust, what to discard. That stack of decisions is what forged the current form of this 40-kilogram machine. Moving forward, the choices to trust or discard will continue. That relentless, unglamorous grind is the only way to carve out a new path. That's what I believe. Thank you for watching.